Okay, so we see an explanation here, and I think I posted the videos of this back in March when Brian and I did this. Brian's now observing the course and is always available to answer questions in a way that's maybe less confusing than the way I would answer them. I don't know, maybe more, so you pick and choose. Okay, but I think Ryan understands this as well as I do. So, we're looking at the integral of a function, and the function would be, well, it's an f of xy dot dx, or could be a dr there, just the same integral we just looked at, and we express that as some function times dx plus another function times dy. Okay, so ds is basically dx times I plus dy times j. F is an m times I plus an n times j. We do this dot product and we get this. There's no big mystery about this. We're integrating around a closed curve. We start by looking at the integral well, you got a sample point x star, y star within a small rectangle. We denote this corner by x naught, y naught. That's an arbitrary notation. We have a delta x by a delta y, and we integrate this function around this rectangle. And we're going to relate that to an integral of the same function over the surface. Okay? And we'll work out the details. Okay, so we start with a statement of Green's theorem. Now I actually want to use the same notation your book does. I want to make sure I don't have my letters backwards, and I should have looked earlier, but I didn't. So I'm going to have to digress here a little bit and come back to your course. And here I have it. And then I'll look at the e-book, which takes a little bit of time because unfortunately I don't have a hard copy handy. Hard to get that from a publisher now, although I'm sure they'd send me one. So actually, this is an OpenStax book, and you'd think I'd remember that. And I do have a link to it, but I can get this by looking at Green's theorem. Yeah, and your book uses P and Q rather than N and N. Okay? So, I want to keep the notation familiar to you. So we have Green's theorem, which says that the integral over any closed curve of a sufficiently well-behaved function f dot dr, and they do use the dr notation, equals the integral of p dx plus, it's q, right, p and q dy, and that equals, now this is equal by definition. Okay, there's nothing mysterious about why this equals this, although I'll write it out in a minute. Okay, this equals the integral it's a double integral over the region bounded by the curve of qx minus py, and then it's dA, where A is your area. It could be dy dx or dx dy. Okay, let's flesh it out. Where F equals pi plus qj, and of course R equals xi plus yj, and we might have to parameterize that to do the integral, and dr therefore equals dxi plus dyj, so that f dot dr equals p dx plus q dy. So that this equality, as I said before, is pretty much automatic. Now this one takes a little bit of work, and that's where we got to start looking at that little rectangle. Okay. And also, dA, your area increment, is just this. Okay, so we consider a small rectangle. By delta x by delta y. Oh, one other thing. D is the plane region, and I just realized I don't have the camera. And that looks like this. This is the plane region, okay? D is the plane region. Bounded by C. That turns out C has to be orientable for this to make sense, but we'll talk about that later. Just assume that, you know, regions are like the ones we've seen that are pretty much always orientable. But you've seen that question, and it's one we need to talk a little bit more about as we move through this stuff. Okay, so again, maybe I didn't. Maybe you should have screamed, but you might not have seen this, so let's just say it again. Here's Green's theorem. I'm probably writing this where you can't see it. Yeah, you can pretty much see it. This is Green's theorem. For the certain restrictions, pretty loose restrictions, but they're important, on the curve C, like it's got to be orientable, so it's got to bound some region. We have this, f dot dr equals p dx plus q dy, so we have this. This is line integral of f around the curve. Well, the line integral of the tangential component of x around the curve, okay, equals this, and the big deal is that this equals this, okay? And that's really kind of unexpected. You wouldn't expect a line integral necessarily, unless you thought about it pretty deeply, to equal the integral over the plane region, Okay? They seem like two different things. Why should the integral of the function over the whole plane region be so closely related to the integral around its boundary? Okay, well, good thing it is, and it's a good thing we figured it out, because it was absolutely essential for unifying electricity and magnetism, one of the foundations of our technological society. Assuming our technological society is a good thing, and I do assume that because we might as well assume it because we've got it. Okay, and I really kind of like living in a technological society, although there's some factors there that I'm a little concerned about. We've got to do it intelligently, and I'm not seeing a lot of intelligence out there. At least not a lot of attention being paid to intelligence. We've got to get a little better at that, a whole lot better. Where things could melt down badly within your lifetimes. Okay, so anyhow, enough philosophy. Here we have the situation. We want to see why it is. Okay, it comes down to this. And here's our region. And here's some point within the region. In a typical increment. And I'm not going to go through the partitioning process, but you want to think through that. And of course, we're going to probably do that when we look at this for some specific function. Presumably, there's a parameter space in which we can define the function, parameterize everything, and do the integral. And often we don't need to parameterize anything, we just do it in terms of x and y, if your curve is defined in terms of x and y. Okay, we have dimensions delta x by delta y. Our integral is going to be over what I call path 1, and then what I call path 2, then what I call path 3, and you probably have anticipated this, what I call path 4. Okay? And the key is going to be that if this increment, if delta y is really, really small, then there's not much difference between the integral from here to here and the integral from here to here. Okay? So, very little difference between this, because if your function is continuous and continuously differentiable, there isn't enough delta y to give you a big difference between here and here. Okay, so intuitively this should be obvious. The function is almost the same at every point of this path as it is at points on this path. So I'm going to get a little loose without defining this. I'm going to call C3 the integral over this. Okay? And actually I want to start with C1. The integral over C1 of f dot dr plus the integral over C3 of f dot dr is almost zero. Again, because every point here can be matched by a point here where the function is almost the same. and we're integrating this in this direction. If we were integrating on this path in the same direction, then these two would be equal. Okay, but C3 is integrated in the opposite direction, so the integral over C3 should be very close to equal and opposite the integral over C1. Now that should be very clear. You want to really think about that. Okay, this is almost zero. But not quite. Why not quite? Then I wrote because, and as I was writing it, it occurred to me I'd probably better use the word unless. Now I said use the word unless, and there are several scenarios in which the unless might apply, so I've got to qualify that, and I'm not sure that's a great idea, but I'm going to do it anyway. Unless P doesn't change. Between C1 and C3. Now, that's not quite right. So I'll say unless something really weird that doesn't matter happens, and I don't want to get into what something really weird that doesn't matter happens might be, because it doesn't matter. Okay? So what you want to understand is that if P doesn't change between here and here, then its value at every point here is equal to its value at the corresponding point along a vertical line here. Which would mean, of course, then that this integral, the integral over this path, the integral over this path are equal, and you would get 0. Okay? Unless this is true and something totally weird doesn't happen, this will be almost but not quite 0. Okay? Yeah, I think I said that right. Okay, you want to grasp that. Now, it's almost 0, but not quite, and the not quite depends on how the P function changes between here and here. Okay? Now, why the P function? Because it's the P function that we're integrating with respect to x. The Q function is integrated with respect to y, and it doesn't affect the integral here or the integral over this path. It affects the integrals over path 2 and path 4. So we're just looking at the path 1 and path 3. Well, what is it that governs how P changes between path 1 and path 3? And I'm going to phrase this as what governs the change in P between a point x, y, presumably on curve C1. And a point up here at distance delta y above that point. At least the way I've drawn it, it's above that point. The answer is, it's Py. Okay? Because, of course, all right, since P of xy plus delta y over P of xy over delta y is approximately equal to Py at xy for small delta y. Okay? That's your definition of the partial derivative of any function with respect to y. So here we have it. Okay, so in particular, I said for C1 and C3, and in particular for our presumably tiny region, Py of xy stays close to Py of xi star yj star. So we conclude that the integral over C3 of f dot dr minus the integral over C1 of f dot dr. Now I'm just going to write this out. You might see it and you might not. I wouldn't expect many people to see this, although you're pretty good, so maybe you will. Okay, we conclude that the integral over C3 minus the integral over C1 is equal to, approximately equal to Py of xi star yj star delta x. Why is this? It's because the values of P along this curve minus the values along this curve left something out that was bothering me. We need an area here. So in explaining why this is true, I realize we need the area. Okay. you multiply the py by delta y to get the difference between the function down here and the function up here. That's direct result of this, that p of xy plus delta y minus p of xy is approximately equal to p of xy times delta y. So if you want the difference in the values of p, you multiply the py by delta y. Okay? So, again, I've written that out kind of short, mainly because I'm out of space, but I'll explain that when we go on. Where this leads us is, of course, that your py of xi, yj, delta y, delta x is this. It's going to give us py dA. That's py dA. Now just write that py star for py evaluated at our sample point. Okay? I've also got a wrong sign on this. When I said minus, I'm thinking in terms of changing the value from here to here, but this is integrated in this direction, this is integrated in this direction, and that leads us to a negative sign here, and when I write this out fully, I'll explain that negative sign. But that negative sign is necessary because, of course, you've got a minus py dA. Okay, well, we have this. Okay, and that's really totally neat, and we begin to see how the line integral around here is going to be related to the area, because we've already seen that the line integral contribution of path 1 and path 3 is related to py times the area. So we've sort of demonstrated why we have this part. Well, we can do the same thing for the delta y and the delta x, the delta y increments, the path 2 and the path 4. And we'll see why it comes out a plus qx dA. And we'll go on with this in just a minute.